All right, ready to get started. Sorry about the delay. So today, we're going to finish up our discussion of MapReduce. And we began talking about MapReduce last time. We worked through an example, this inverted index example that's kind of a canonical example of what you do with MapReduce. And today we'll talk about some more examples. And we'll talk about the MapReduce approach to fault tolerance, and we'll talk about some optimizations we can do on the basic approach that we talked about last time. To recap, can somebody remind me from last time, what are the phases of a MapReduce job? Yeah, we got map phase, shuffle phase, and reduce phase. So let's refresh our memory on what goes on here. Let's talk about the map phase first. So this phase is when the programmer supplied map function runs on all the input data. Can somebody tell me what the type of that map function is? That is, what's the type of its input and what's the type of its output? So these are going to be the types that the input and the output have conceptually. They won't necessarily be the actual types that appear in the code that you write. Feel free to look at the paper if you need to refresh your memory on this. So we're trying to figure out what the type of the map function is. What is its input type and what is its output type? Okay. So, I didn't think this would be a hard question. So the input to the map function is going to be a single key value pair. So the input data for the entire MapReduce job is going to be a potentially huge set of key value pairs. And the map function is the code that you want to have run on each one of them. So the input to the map function is going to be some input key value pair. The output from the map function is going to be a set of intermediate key value pairs. Right, so where do these intermediate key value pairs that are produced by the map function stored? Where did they end up after the map function runs? Right, so they are going to be sent to the reduce workers sooner or later, right? But initially they get stored locally. So they get stored in local storage on the map workers, on the machines where the map function was run. So let's actually look at some examples of map functions. I'll come back to this. So last time we talked about creating an inverted index, right? So the input to the map function, recall that, so this is, I'll put this at the top, this is the type of the map function. So for an inverted index, the input would have been a pair of, let's say, a document identifier, let's say doc1, and a list of words in it. So it would be something like this. So this would have been one input to the map function in the inverted index example. And the output of the map function was what in this case? Right, it's going to be something that would look like this. So we would have a mapping from words to document identifiers, and so on. Okay, so that's what we would do if we wanted to do the inverted index. But MapReduce is more than just a distributed fault-tolerant framework for computing inverted indices. It's a distributed fault-tolerant framework for doing lots of things. So what if we wanted to do something else? What if we wanted to do a word count instead? What would we want the map function to spit out then? So let's say that this is still the input. So let's say the input is still of that shape. What would we want the map function to produce if we were doing a word count? Sure, okay. So, So let's say the whole sentence is the quick brown fox jumps over the lazy dog. So there's two occurrences of the in the sentence, right? So one way to do this would be to say, well, the has to be mapped to the number 2. But another thing you could do is just emit a whole bunch of pairs that look like this. The 1, quick 1, and then later the 1, and so on. So why is it okay to just emit 1 here? Because all of the occurrences of the are going to be added together later. So it's okay to defer that adding until after this phase. It's okay to defer the adding until the reduce phase. However, if we felt like adding it here as an optimization, we could. So this would be a completely legal and valid output of the map function. But we could also have something that did some combination. Now, are we done? No, right? Because we still have to combine with word counts that happen on other map workers. But we could do this. We could combine as much as possible locally. And we'll come back to talk about that in a minute. Okay, so that's inverted index and word count. What about something else? What about distributed grep? So let's say that we want to search for a string. Let's say that we want to search for the string dog. Maybe we want all documents that have the string dog in them. What should the map function produce then? Again, assuming that the input is one of these pairs of document identifier and word list. So what would we want our map function to spit out if we were trying to do this distributed grep? So, grep is spelled with a P. So in this case, what we're trying to do is we're trying to figure out what documents have a given word in them, and maybe we even want the context in which that word appears, right? So instead of just saying, oh, well, dog occurs in document 1, we might want this piece of text that says lazy dog. Or if we have a document that says, I love my dog, Spot, then maybe the output we would want would be something like this. Or it could be the whole document if we want. So it depends what we want, right? It depends whether we want different results for different occurrences of this pattern dog, or if we want one result for every document that has any occurrences of pattern, right? So if dog occurs at several places in the document, do you want that document to just appear in the results once, or do you want individual occurrences of dog in the document with the context around them? So if the input had been like, I love my dog Spot, who is the best dog ever, then the output might be something like this. So this would be the set of intermediate key value pairs that would be produced as the output. Okay, so that's a bunch of examples of map functions. What happens after the map phase? The shuffle phase. What's the shuffle phase? What happens there? Yeah, so that's when the data from every map worker, the result of running this map function, this set of intermediate key value pairs, that's when that data goes onto the reduce worker that will process it. So I wrote the appropriate reduce workers here. So how is it decided which intermediate key value pairs are going to go onto which reduce worker? Yeah, so it's going to get decided by what's called the partitioning function, which does something like hash of the key mod r, where r is the number of the reduce workers. So interestingly, in the paper, they don't actually say that the default partitioning function is hash of key mod r. They say that there is a default partitioning function that's used to distribute data onto the appropriate reduce workers. And they say that it uses hashing. And then they say, for example, hash of key mod r. But they don't actually come out and say that that's actually it. So maybe Google has some secret partitioning by hash approach that they're not telling us about. But it's probably something a lot like hash of key mod r. By the way, somebody just asked in chat, what's grep? Yeah, so grep is, let me actually look up what grep stands for. I don't even know. So grep is probably best known as a Unix command line utility for searching for lines of text that match a regular expression. So according to Google, grep stands for Global Regular Expression Print. I did not know that until just now. So grep's for searching for text that matches a regular expression. In this case, we were searching, like in this example here, we were searching for documents and places in documents that matched this regular expression dog, and we were saying that there was some context around the matched expression that we wanted to keep. So depending on what you wanted to do, you could ask for what are all the documents that contain the string dog, or you could ask for what's the context in the documents that contain the string dog. This is obviously something that that Google might be interested in. All right, so back to this. So we talked about this a little bit last time, but I want to run over it again. So at the end of the last lecture, we talked about why they did this instead of using consistent hashing. Because as we've discussed a number of times now, doing hash of key mod r doesn't work great as a way to divide up data if the number r ever changes. So r here is the number of reduce workers that they are. More generally, it would just be the number of nodes that you want to partition data onto. So this isn't great if r ever changes because it means that data needs to get moved around. But why is it okay to do that in the setting of MapReduce? We talked about this a little bit last time, but let's just recap it. Why is it okay to do this as the partitioning function in MapReduce? So let's think about the context here. So the reason why we didn't want to do this in the setting of, say, Dynamo is that if a node added, or if a node joined the ring, or if a node left the ring, either because it failed or maybe you took it away on purpose because you needed those resources for another reason, then the place where an existing key hashes to is going to change, because hash of key mod 4 is different from hash of key mod 5, let's say, which means that a whole lot of data would move, and unnecessarily so, right? So we talked about consistent hashing as a way to ensure the minimum of data movement when nodes left or joined the set of nodes onto which you're partitioning data. So with MapReduce, I think the reason why this is okay is because R doesn't change, right? So this is an offline system, not an online system. So with consistent hashing, we do it because we always want to be responding to client requests, right? Whether or not a node dies, or whether or not we're adding new nodes, it's not like we can stop responding to client requests just because we need to add a new node to the system. So in that situation, it's worth taking the time to make adding or losing nodes as non-disruptive as possible. But with MapReduce, the reduce workers are not serving client requests, right? Is somebody going to come along in the middle of the MapReduce computation and say, oh, here's another piece of new input data that you're going to handle? No. There's an assumption that at the time you begin the computation, you already have all of the input data that you need. That's why this is batch processing, like we talked about last time. So the MapReduce framework can make a smart decision about how many map workers, well, it might ask you to specify like how many map workers and how many reduce workers you need. But it doesn't, you, the programmer, okay, I guess the MapReduce framework decides how many map workers are needed. You, the programmer, are expected to make an informed decision about how many reduce workers you need. And if you chose too few and your job is taking longer than you'd like, too bad, better luck next time. But the assumption is that since you have all the input data to begin with, you're not going to be adding more map or reduce workers to the system in the middle of a MapReduce job, in the way that you might have to add more nodes to Dynamo to handle an increased load of requests from clients, or just to store more data. So adding more nodes beyond the originally planned number during a job is not really a thing in MapReduce. And so that's why this number doesn't change. We don't have to worry about this number changing during the job. And so this is an okay way to partition data. So by the way, though, what about crashing, right? What about when MapReduce workers crash? How does the MapReduce framework handle that? Does anybody remember from the paper? Yeah, so somebody just wrote in chat, assign its jobs to another machine. Okay, but who does that? Who is responsible for knowing what work the failed machine was doing and then assigning its jobs to somebody else? The master, right. So MapReduce involves a machine called the master. And this is actually a very important piece that we left out of the picture that we drew last time. So if you consider the picture that we drew last time where we had some map workers on which some computation took place, and we had some reduce workers over here, and we had our shuffle, so this isn't actually all the machines that are involved in MapReduce. There's also going to be a master up here whose job it is to know who all these other machines are and assign work out to them and have some idea of who is alive and who is dead. So the master is actually talking to all of these machines. So the master is responsible for assigning out tasks to the workers. And it pings them periodically, right, to see if they're still alive. If it doesn't hear back within some given amount of time, it's going to assume that they've failed. And the master knows what tasks are assigned where. So if a worker fails, the master will reset the task that that worker was working on back to unfinished, and some other worker will have to step in to replace it and be assigned that task. Okay, so let's talk about this concept of failure for a second. So let's say that a map worker fails. So if that happens, if a map worker fails, do you have to start its tasks over from the beginning? Yes, you actually do. Because why? Well, because it stores its output. Remember, we say it stores its output, those intermediate key value pairs, on its local disk. And that's an important aspect of the MapReduce framework, right? That it just stores those things locally, which is cheaper to do than sending them over a network. But because it's just storing those things locally, if it dies, that disk is going to be inaccessible if it crashes. So all of the work that it did and stored locally has to be redone. So this is a trade-off that MapReduce makes. The design of MapReduce makes this trade-off. They could have said that this map worker has to store all its intermediate data on GFS, on the distributed file system. And then if it were stored there, then it would be accessible even if the map worker died, right? But that would take more time than storing it locally. So they considered the pros and cons, and they decided that the right thing to do was to store data locally and occasionally have to pay the cost of recomputing that data rather than store it on the distributed file system and not have to pay that recomputation cost. But instead having to pay this upfront additional cost of having to put everything on the distributed file system. So distributed systems are full of trade-offs like this, right? And so this is an interesting aspect of MapReduce. One of the hallmarks of MapReduce, I think, is that it makes the choice of redoing work quite often. So if a map worker fails, all its work must be redone. And this is not necessarily the wrong choice, right? Like that sounds like a bad thing written out like that, but the alternative would have been to store its work on the distributed file system, which would be expensive to do and maybe not necessary if crashes are rare. So in MapReduce, they often make the choice of redoing work like this. That's their approach to fault tolerance. Remember how we said earlier in the course that fault tolerance often involves making copies of things, right? We said replication of data, right, is one manifestation of that. So creating replicas is one manifestation of that. Resending messages so that you get reliable delivery is another manifestation of that, making copies for fault tolerance. And another is replication of computation or redoing computation, and that's the choice that MapReduce often makes. Okay, now reduce workers recall that they actually do store their output on GFS or whatever it is whatever distributed file system is being used. So if a reduce worker dies, its tasks don't have to be re-executed. That output is going to be readily available. This is kind of an interesting point, though I'll come back to this later. Okay, so we've talked about the map phase and the shuffle phase. Onto the reduce phase. So the data has gotten onto the reduce workers now. The reduce function can run. We talked about the type of the map function conceptually. Can somebody tell me what the type of the reduce function would be conceptually? So the reduce workers they're each going to have their own partition of the data, right? The data that got hashed onto them. So every one of these intermediate key value pairs that had the same key is going to end up on the same reduce worker, right? And it's the job of the reduce function to put them together. So we could say that the reduce function we could say this. We could say that it takes a set of key value pairs with the constraint that all the keys are the same. But instead, the way that they express this in the paper is they say that the reduce function takes one key and a set of values that go with it. So they say reduce takes a pair of a key and a set of values. And it produces a set of output values. So let's see some examples of that. So for the inverted index that we talked about, let me bring up that page again, which I dropped on the floor. So here's inverted index. So what's going to be, so this was the type of the map function for inverted index, or this was an example of inputs and outputs for the map function for inverted index. What would it be for the reduce function? So for the reduce function, so this was for the map function. For reduce, what would it look like? Well, an input to the reduce function would be what? For the inverted index example. You probably have this in your notes from last time. Okay, so let's talk about this. Maybe people are a little bit confused. So these are going to be the intermediate key value pairs. Recall that what we're trying to construct is something that will let us look up, okay, what are all the documents that contain a given word, right? So the input to the reduce function is going to be a key, like so conceptually, right? it's going to be, so this is what it would look like in reality, right? It might be like the occurred in document 1, and the also occurred in document 3, and so on. And then that would get brought together into this list, right? But we just said that that we should think of the type of the reduce function conceptually as already being this, right? We should think of it being as a mapping from a single key to a set of values. So this, conceptually speaking, is already the input of the reduce function. And so conceptually, the reduce function really doesn't have to do much at all. It just writes its output out to the distributed file system, basically. So in practice, you'd pass it an iterator, and it would have to iterate through the values and do something with them, right? But the thing it does with them could be as simple as just writing them out to GFS unchanged. Okay, so what if we were doing word count? What would the input to the reduce function look like then? So recall that reduce maps a particular key to a set of values. Or the conceptual input type of reduce is a particular key and a set of values. So what would it look like for word count? Right, yeah, it might be something like the 1, 1, 1, 1, 1. Because the map function emitted the and 1 every time it saw the word the, right? Or if it had done this optimization, maybe you would have some other numbers in there. So you might have like the 1, 2, 1, 3, 3, etc. So what does the reduce function do with this? It just adds them all together. So it would output something like the 5. And that would be a count of every occurrence of the in every document. The is pretty boring example. I should have done some more interesting word. But that would be what the output of the reduce function would look like for word count. So here, whoops, it's getting quite messy here. But hopefully you begin to get the idea. What about the distributed grep example? What's the input to the reduce function then? Well, it would be something like document 1 my dog Spot, best dog ever. So that would be the input to the reduce function. Recall again that reduce function maps a particular key to a set of values, and then the reduce function would just output its input. This is actually pretty common for the reduce function to not do anything interesting. So I find this kind of fascinating. So we said, in MapReduce, we have this communication pattern, right? This all-to-all communication pattern where work gets mapped onto the appropriate reduce workers. But a whole lot of magic, I think, happens in that mapping onto the reduce workers, right? Because since the intermediate key value pairs that are produced by the map workers get partitioned on the reduce workers by key, that's kind of where all the magic happens. And if the job of the map, like if the work that you're trying to do largely consists of splitting these things up by key, then by the time you get done shuffling them onto the correct reduce workers, you've already done that. So it's actually pretty common for the reduce function itself to not have to do much interesting. All of the magic happens in this shuffle phase, where all of these key value pairs get collated by key. Questions about this? Somebody asked me to look at this again. So yeah, for the word count example, so we're saying, so our input is these pairs of documents and words, right? On the map function, the map function is going to produce either just this list of pairs where it's every word that was in the input and the number 1, or if it's doing a clever optimization, it might do some combination of the values. So if a word occurs more than once, then the count over here would be the number of times that it counted locally. So then conceptually, the input to the reduce function, so a given reduce worker is going to deal with all of these intermediate key value pairs that had a particular key. Let's say it's the word the or the word dog or whatever. So conceptually, the input to the reduce function is going to be that key and then everything that was paired up with that key, whether it's just number 1s if you didn't do the optimization, or maybe it's some other numbers if you did. So there would have been many documents actually. And so this might have been the result from this one particular map worker that was dealing with document 1. A different map worker would have dealt with document 2, maybe, and a different one would have dealt with document 3. But all of those, any occurrences of the same key, the word the or the word dog or whatever, would get sent to the same map worker. And so that happens as part of the magic of the shuffle phase. So, which I don't really mean to describe as magic, it's really just hashing. But we called it a communication pattern, but it's actually important to the computation as well, because it causes those records that had the same key to get collated together in the same place so that now we can easily add these numbers up. So somebody just asked on Twitch, who's responsible for transforming the output of the map function to the input of the reduce function? Okay, so yeah, so the output of the map function, you might ask, like, if this is what the output of the map function looks like, which is these intermediate key value pairs, but the input to the reduce function is supposed to look like this, who's responsible for turning this into this? So let me say again, this is the conceptual type of the input to the reduce function. In practice, what you would get is a key and then like some sort of iterator that would iterate over these values. So it wouldn't. So all the data is there on the reduce worker because it gets sent there by the shuffle phase. And so in principle, this is the type of the thing that you have. Whether there's actually something in, like, not even, like, whether or not there's anything in memory, let alone serialized out to disk, that actually looks like this is another question. There probably isn't. But conceptually speaking, this is the type of the input of the reduce. So I'm glad we've been talking about word count here, because this kind of gives us an in to talk about this this particular optimization that's interesting. So this word count example is really screaming out for this optimization, right? Where different keys, or where two keys that are the same get combined, right? So let's say that I'm a map worker and I have to count occurrences of the word dog. So we'll say that maybe the document that I'm working with is like, my dog Spot is the best dog and the fastest dog. So if I used the naive version of the word count map function that appears in the paper, then it would emit these intermediate records. And then during the shuffle phase, all of those would end up getting sent to the same reduce worker because they have the same key, and then added together on the reduce worker. The trouble with doing it that way is that it wastes bandwidth, right? So they could have just been added together on the map worker's side, and then the map worker could have just been sent, or could have just sent this over to the reduce worker. And then that would be added together with every other map worker's count for the word dog. So the reduce worker would still have to do addition, right? But they would be adding together these subtotals, right, from all of the map workers, instead of just adding up a bunch of ones. So doing this on the map worker, doing as much combination of the intermediate key value pairs locally on the map worker is called using a combine function. And a combine function is actually just the same as a reduce function, except that it runs on the map worker, and it's a way of doing some work in advance. So why is this okay to do? Why is it safe for us to take some of the work that the reduce worker normally would have done and do it early on the map worker? Why is that legal for us to do? In the case of this word count computation, let's say. Yeah, so somebody just said in chat, because it has no effect on the rest of the distributed result. Okay, sure, okay. Why does it have no effect? So I would say the reason why this is okay to do is because addition is associative, right? That is, if you add A plus B, and then you add C to that, then that's going to be the same as adding A to the result of adding B plus C. It's the associative property of addition. If the reduce operation that you're doing is associative, then it's okay to do as much as you can early. In other words, locally on the map workers. And the reduce workers will still have work to do, right? They'll still have work to do, but not as much data will have to be sent during the shuffle phase. So instead of sending the pair dog1 1,000 times, instead you can just send dog and 1,000 to the relevant reduce worker. And the reduce worker will then add that number 1,000 together with the totals that it got from the other map workers for dog to get the final result. But it's just fine to do this addition early because it doesn't make a difference in the output. Now, it might not necessarily be the case that every reduce function is associative this way. And so if that's true, then you can't do this optimization. But for something like word count, you certainly can. Questions about that? All right, let's talk about the quiz question from last time and then do a quiz question. Yeah, so here was last time's quiz. So we asked, what happens during the shuffle phase of a MapReduce computation? So the answer we were looking for here was, this was the place where the intermediate key value pairs that were produced locally on the map workers get sent to the appropriate reduce worker via some sort of partitioning function, such as hash of key mod r, where r is the number of reduce workers. That's what happens during the shuffle phase. That's when data gets sent to the appropriate reduce worker. And here's a quiz question for today. Yeah, so somebody just asked a question in chat, which was, can the reduce function output a set instead of a single value? This was just asked on Twitch. Yeah, we were talking a second ago about the types of map and reduce in the MapReduce framework. So yes, we do think of the output of the reduce function as being a set. This is, if you're familiar with the notions of map and reduce from functional programming, then this might sound a little strange, right? So I actually want to, after a minute, when we get a couple more quiz responses, I want to talk about the difference between these types in MapReduce and what we normally think of when we're doing functional programming. So I'll give it like another minute or two here. Somebody else asked in Slack or in Twitch chat, if there were no combine function, then would the map worker send this pair of dog and the number 1 3 times to the reduce worker? Yeah, it would. So that's one of the things that a combine function could do, would be to do that work earlier. All right, it's a pretty good response rate. Let's move along. Yeah, so the question that was just asked was kind of anticipating the very last thing that I want to talk about. So in MapReduce, these are the types of the map and reduce function, at least conceptually. So the question that was asked was, does reduce produce one value or a set of output values? Well, in MapReduce, it produces a set, which might look a little bit strange if you're if what you're used to is like the traditional definition of reduce from functional programming. So let's talk about the traditional definitions of map and reduce. Just briefly, I'm a programming languages person, so when talking about MapReduce, I would be remiss if I didn't spend a little bit of time talking about this. Okay, so what's the type of a map function traditionally? So a map function is something that takes a function and a list, and it applies that function to everything in the list. So if we were writing this down in Haskell, we would say it takes a function from A to B. So this is a function and it takes a list of A's and it produces a list of B's. And we're not, even without writing down the definition of map, we can kind of see what's going on here, right? If we have a list of A's, whatever they are, numbers, whatever, and then we have a function that takes things of that type and turns them into another type, then we can take everything in that list, apply the function to it, and get a list of the output type. So in Haskell, it would look like this. You would write, the implementation would look like this. One possibility is that the list here is empty, right? So if this list is empty, right, the output list is also going to be empty. So in that case, we don't care what the function is. And so you typically write, in Haskell, you would write an underscore to show that you don't care about that argument. So in the case where the input list is empty, this is an empty list in Haskell, then the output list is also empty. That's that case. That's the boring case or the base case. And in the other case, you have some function f, and then you have some list, which has a head and a tail. So it has a first element, which we'll call x, and then the rest of its element, which we call x's. And then what you do is you create a new list that just applies that function f to x. And that's the first thing in the list. And then you stick that on to calling map recursively on the rest of the list, again passing in the function. So this will be a recursive call. This will go and eventually you'll get to the base case and then you'll be done. So for example, if you were to call map of, let's say increment and the input list was 1, 2, 3, then the output would be 2, 3, 4. So that's an example. What about reduce? So really briefly, reduce, or as it's sometimes known, fold R, is going to take a function that's going to take an A and a B and produce a B. It's going to take a value of type B. It's going to take a list of values of type A, and it's going to take and it's going to return a value of type B. So notice that it returns a single value, not a list. So what does this do? Well, if you have a list of A's, and if you have a function that takes an A and a B and produces a B, how are you going to run that function? Well, you need a B. Thankfully, you have one right here. So this is your B. So that B is going to be useful. This is what we call the sometimes you might call this like the base value or identity. So the implementation would look like this. If you're reducing and this input list A is empty, just like we saw with map, if the input list is empty, then it's easy, right? So if this input list is empty, you can't run this function, right? Because you don't have anything of type A because the list is empty. You were supposed to produce a B. Oh, look, you have a B. So you can just give back that B that you got. So we don't care what this function is. We have our base value or our identity value, or sometimes called our zero value, so often traditionally called Z, and the list here is empty, and then this is Z. So that's the base case. Here's the recursive case. So reduce takes a function. That's this function here from A to B, from A to B to B. We have our zero value Z, and we have our list which is not empty, but has a first element X, and then the rest of it is X's. What do? Well, we're trying to create this B, right? So what we can do is we can take our function f, we can apply it to X, which is an A, and then we need another argument, which is of type B. How do we get a thing of type B? With a recursive call. So that's what the implementation of reduce looks like. None of this is necessarily relevant to the course. I just felt as though I would be remiss if I didn't talk about this when, as a programming languages person, when I'm teaching MapReduce, I should talk about what MapReduce means to me as a PL person. So an example of this might be, well, we talked about word count, right? Word count was an example of adding together a bunch of numbers. So you might do that with reduce, right? So if your reduce was like, let's see if I can put together an example quickly here. So you might say reduce, and then the function you might pass in here might be like add, and this is like, let's say like a binary add function that takes two numbers. The base value that you might pass in would be 0. And then the list of numbers that you would pass in, let's say it's like 1, 1, 2, 1, something like what we had in our word count. So what's going to happen? Reduce is going to go through and add those things up. And then the result will be 2, 3, 4, 5. Which was the same type as this, which was what it was supposed to be. All right, there's your brief introduction to Haskell for the day. That's all I have to talk about. I think we're through with our discussion of MapReduce. We don't have class on Friday because Friday is our hack day. I have office hours after this, so come talk to me if you have questions. And Monday is a holiday. So I will see you again next Wednesday. Take care.